In this module, we will discuss this additive manufacturing of porous scaffolds for bone tissue engineering applications. So, what I will give some brief idea about what is the different scaffold fabrication techniques, that is solvent casting and particulate leaching. Second one is electro spinning, and third one is the rapid prototyping techniques. So, the solvent casting or particulate leaching, it is a very common technique. What you do here, you start with a particular polymer which is the base polymer, you use some porogen. This porogen can be some sacrificial agent like sugar or kind of salt crystals and all, NaCl crystals and all, and then after you add this, then you put it in the water and then you see that how this leaching takes place, and after this leaching is done, then it gives you a porous scaffold. This is a typical example of a porous scaffolds which is made of the hydroxyapatite. This is from our own research. As you can see, the pores that is forming here, these pores are of different size. And if you look at the cancellous bone structure, which is highly porous, there the also pore morphology is not uniformly identical for all the pores, but there is a distribution of the pore size and pore shape into the scaffold, and that is what is very typical of any biological origin materials like cancellous bone, for example. The other things you do we do notice here, that is called pore wall width or the strut width. Then again that very nice strut width also you can see that is also different. If this is the 200 micron, so this is like 50 micron or so. Now this strut width is important. Why strut width is important? Because that strut width will determine that what is the mechanical strength properties of these materials, how fast this porous scaffold will collapse under load. If the strut width is very small, then this scaffold cannot experience or cannot sustain higher mechanical load. Now this solvent casting and this kind of scaffold processing technique can be applied to different materials like polylactic calculoric acid, polylactic acid and so on and so forth. The second one is the electro spinning technique. Electro spinning is what, that you take the polymeric precursor solution in a syringe pump here, and in a syringe pump then you make a Taylor cone, and this Taylor cone then you make it this kind of unstable, then it forms that unstable Taylor cone, and then that will form then that will be deposited either on this kind of rotating and translating collector, or it can be deposited simply on a plate, receiver plate. Now this is essentially shows that how these capillary forces are important, and it forms a cone, and this is also with increasing applied voltage, like voltage you essentially apply between the syringe pump and the collector plate. Now Taylor cone formation is a fundamental importance in the process of electrospinning, and it essentially originated from the electrostatic force balance and then surface tension of the liquid. This is some of the examples of the electrospun scaffolds. This is again from our own research result. This is a carbon nanofiber scaffolds, and what you see on the right hand side is that some of the neural cells which have proliferated on the scaffold. The blue stained region is the Duffy stained nucleus of the live cells, and the green stained region is the actin, and you see these actins, they are kind of oriented very nicely on this kind of fibrous scaffolds, and this essentially that fibers will provide certain kind of physical anchorage, or fibers will provide some kind of physical structure on which that actin cytoskeleton can reorient and reorganize and can expand on the surface. Now coming back to the rapid prototyping technique, the fundamental definition of rapid prototyping must include that layer by layer deposition techniques, that is the generic description in whatever rapid prototyping technique that you are using, whether it is for scaffold fabrication for biomedical application, or whether it is for structural applications like a dense component, non-porous component, everywhere these things is used. Two techniques has been mentioned here, one is a stereolithography and one is a selective laser sintering. What you see here in the stereolithography, your laser is focused on a scanner system, then when the object being fabricated here, that you can put it here, and there is a vat and photopolymeric solution is there, and there your structure would be fabricated in a layer by layer technique. Second one is a laser selective laser sintering. You start with a powder bed, you focus your laser system here and on the structure, then powder bed will be moving one layer by one layer, and then it will be heated up, then it will be sintered and solidified in this selective laser based sintering techniques. Now, in the 3D printing technique, again you start with a CAD design. So, that is computer aided design, you make the stereolithography file as an input file, then you have a build piston and you have a post processing. Okay. So, in the build piston and post processing, what you see here, that how this structure is being built and then further how it will take a particular concept. So, this is some of the examples of this 3D printed structure like polycaprolactone based mandibular condyle design fabricated by solid free from fabrication. SFF stands for solid free from fabrication, and also PEG polyethyl glycol based scaffolds like salt leaching and prepared by bioplotting. Now, in the context of biomedical applications, these additive manufacturing or 3D printing based techniques have received wider attention or have received have attracted lot of attention simply because that bone is a natural biocomposite which is made up of hydroxyapatite and collagen, and bone has different varying porosity in the structure, and this gradient porosity varies from cortical to cancellous side, and this cortical to cancellous side, that pore shape, pore size and their distribution as well as strength also depends on what is the anatomical location of the structure. It is very difficult to mimic this kind of gradient porous structure in any artificial synthetic materials, and this gradient porous structure is what drives this 3D printing to adopt in case of the tissue engineering application. Now, in more is the tissue engineering applications like in the this is called biofabrications. Why is the bio? Bio word is used simply because you are using certain growth factors and then cells together with that materials itself from which you are making the scaffold during the fabrication itself in situ. That means that with the help of growth factors and cells or osteoblast cells like bone forming cells for bone tissue engineering. Now, these cells can be any type, and you give some external cues like you can give some electric field stimulation or some mechanical stresses or mechanical, or you can give some fluid shear for the cartilage applications, or you can give some mechanical stress applications for the bone applications during the shear biofabrication of the scaffolds. So, in this unique approach you can integrate both the cells growth factor, so that growth factors can stimulate the cells towards that more functionalized form, and that is what is been shown here. Once you make these scaffolds if you can see in the 2 dimension, their cells are also interconnected with each other. So, cells are kind of very much integrated into the scaffold structure, and that is what is more important. Why porosity is important in the 3D scaffold? If you see that this is a rectangular strut here, and this rectangular strut, once you give the scaffolds, then you are essentially there is lot of pore spaces in between, right. In these pore spaces what you see is sequentially that as the arrow is going down, that means you are essentially culturing them in a 3D bioreactor with some angiogenic factor of certain scaffolds, and with the help of this angiogenic factor blood vessels they form and then get penetrated, they are penetrating into well into the porous architecture here. So, essentially you are facilitating vascularization process and angiogenesis process together in these 3D scaffolds, but one cannot arbitrarily change the porosity fraction. For example, the increase in pore size and pores percentage porosity promotes new pore formation, but at the same time significantly reduce the mechanical properties. So, just to give an example, if the porosity increases from 32 to 62% in one of the implantable bioceramics, that is tricalcium phosphate, then your strength goes down order of magnitude from 37 to 0.43 megapascal. So, it comes down from 37 megapascal to less than 1 megapascal when the porosity increases just double 32 to 62%. Now, this vascularization or angiogenesis process has been more described here. As you can see that vessels that forms, these vessels are also of different size. these vessels are smaller size, but some of the vessels are larger size. So, you have some primary vessels and you have some secondary vessels which are of much thinner size. So, the idea is that by providing different pore size and shape, you are essentially allowing this random distribution of different sized capillary vessels, because capillary vessels are also will not have simply same size, and therefore, they need to be accommodated in this vessel structure. So, before we discuss little bit more specifically on the 3D printing or some of the additive manufacturing technique, let me just show you some of the other competitive techniques or other competing techniques like electron beam melting, stereolithography, fused deposition modeling, that is FDM, and selective laser sintering, that SLS. So, in all these techniques, as you can see that there are certain disadvantages what has been mentioned. For example, very high local temperature, or fused deposition modeling is only limited to thermoplastic polymers and so on. So, these kind of techniques, and that gives some idea, that gives some rationale for the use of 3D printing, which essentially uses two beds. One is that feed bed, that what is the powder bed. So, this is called F, and this is called build bed, that is that where the scaffold is fabricated in a layer by layer process. And you see this kind of cartridge, and this cartridge, if you zoom it up, see that what is happening here, you put your binder in the cartridge. Okay. So, this binder, it is now forced to get into the orifice. Now, you can see that more expanded part, this once this binder gets out of the orifice, it forms a large tail, and towards the end of the tail, towards the end of the ligament, you see that it can disintegrate very easily once it is elongated to a larger extent, simply because there is two forces that is acting here, one is viscous forces and one is the surface forces. Now, therefore, certain fluid mechanics terms will also come into picture because of your 3D powder printing, and there it forms a satellite small drops, and these drops will descend and then they will interact. Now, what are the factors that which will actually are important for determining the binder properties? One is the pH, second one is the thermal conductivity, third one is the viscosity, and fourth one is the surface tension. So, these binders, once this droplet is ejected, then it will be integrated into the powder. So, from the fluid dynamics part, there are certain dimensionless number which most of the mechanical engineers are aware of, that is, one is the Reynolds number, and Reynolds number essentially the ratio between the inertial and viscous forces. Then there is called Weber number, that is essentially ratio between kinetic energy and surface energy, and third one is that Ohnesorge number. This Ohnesorge number is kind of more important, and Reynolds number is equally important, as I will show you in the next slide. So, Ohnesorge number is essentially describes the relative importance of the viscous and surface forces. So, Ohnesorge number, and fourth one is the bond number, that is a gravitational force through the surface tension force. So, in this particular case, Ohnesorge number, once it is plotted against Reynolds number, it will give you certain printable fluid characteristics. So, what I am trying to say, that binder properties is very important. A binder which will have an optimum combination of these two dimensionless number, what is called Ohnesorge number and one is called Reynolds number, those binders can be printed. So, that your chemistry or your binder formulation need to be tailored to that extent, so that it will have a particular combination. For example, Ohnesorge number should vary between 1 to 0.1, whereas Reynolds number can vary between a large area between somewhere between 5 to 200 or 300. So, within that range and this particular area, that is what is called printable fluid. You cannot arbitrarily select any binder, and you do not expect that binder will be optimum for printing that particular material. Here again, as I said, that this ligament that is formed and then ultimately disintegrated to the drop, this ligament characteristic is what we call tail length. So, this is your tail length here. This tail length, how it will be dependent on the surface tension forces, as well as the viscosity of the material, and you say that surface tension and viscosity they have a different opposing trend. So, if you increase the surface tension, then your tail length decreases. If you increase the viscosity, your tail length increases. So, what it means, you need to have a balance between these two competing terms like surface tension and viscosity, and that leads to a very printable binder formulation. Some physicochemical interaction. Physicochemical interaction essentially means that once your drop comes here and then this is a powder bed, the drops first to be weighted. So, there should be weightability of the powder with that binder. Once it is weightable, then drops can be integrated into the powder bed and then this will dissolve. So, it has to be dissolved like some chemical interaction. So, this we call physicochemical interaction. Okay. So, this physicochemical interaction is very important, that should go into the slide title. So, chemical interaction will lead to the more effective interaction of the powder with the binder. Now, little bit qualitative description of that. Now, if you have the binder droplet here, if you droplet diameter, and if you just this is your time of printing, okay, along the x axis, along the y axis is that drop diameter, binder drop diameter, and if you plot it there, then what you see here, you see that this kind of different variation, and also there is a capillary spreading rate. So, in one case your capillary spreading rate you can see here, and in another case when it is follows this red one, then simply it will retract and oscillate. So, it will not give rise to effective interaction. So, what it will be interesting for us, whether this is what I have put a right mark. So, the droplet will change in increase in diameter, and as you can see here, this droplet will increase in diameter, droplet will increase in diameter. Once drop will increase in diameter, that will give rise to more capillary driven process, and this capillary driven process will be more useful for effective interaction of the binder with that of the powder bed. This entire thing has been summarized in our recent review paper, which is published somewhere this year in Materials Science and Engineering R. Now, this once you make these 3D scaffolds, the next level of interaction next level of challenge comes, that how you characterize this 3D printed scaffold. One of the characterization tool is called microcomputer tomography, and this microcomputer tomography we have this very large facility in Indian Institute of Science, which is from VARSA XRM 400. So, essentially this microcomputer tomography involves very high energy X-ray beam, like X-ray beam here the energy is around 70 kV, just to give you some numbers. And typically if you do that X-ray diffraction technique, in the X-ray diffraction technique it is essentially the accelerating voltage of the X-ray beam is around 20 kilovolt. So, here you are using that very high energy X-ray beam, and then this particular technique is essentially based on X-ray adsorption based technique. So, this is that X-ray adsorption based technique, this, and then you have a 3D scaffold here, and then it comes this sample, and this is rotated in 360 degree, this scaffold will be rotated in 360 degree. So, each time that X-ray beam will come, it will make at the detector some 2D slice. Now, these 2D slices, as I am showing in the next slide, these 2D slices it can be stacked. So, several 2D slices can be stacked in the Z direction, and once you get into the Z direction, then it will make this total scaffold in these materials. So, one of the important things that I must highlight here in the micro CT, the image acquisition is not that difficult. Only thing that you have to play around with that what is that typical accelerating voltage, what is the resolution that you want, and so on and so forth. What is much more difficult, and I have put it in a different color, that is image processing. Image processing means how you can get meaningful data out of that micro CT results, and that requires extensive expertise in the image processing software and so on. So, I will show you some of that work from our own group, so that you know that how to make these scaffolds in real life. So, first thing is that how to conceptualize the design aspect at the beginning. So, this design can be whatever predefined design or it can be patient specific CT data. So, let me repeat it. So, predefined design means like it can, you can just get it, or it can be patient specific design. So, patient specific design means from any part of the diseased part where you want to make, where you want to put your implant. So, you can get the CT data from that implantation sites, and then you can give that STL file to the 3D printer. Alternatively, if you are developing new material and trying to see that whether this new material can be printed using 3D printing, you can use some of the simplistic design file like these ones, and this is what we call predefined design file. Like you are defining that your design file at the beginning with certain pore shape and certain pore size distribution. So, for example, your dodecagonal shapes is like this, your octagonal pore shape is like this, and then you can see that it can be uniform distribution like along this length and along this length, pore size all are same, both along the radial as well as that along the height direction. The other thing can be, you can also gradient the pore size like along this direction, as you see that pore size decreases as you go along this direction, or you can have one of the solid structure and one is a porous structure in both the ends. So, solid structure and porous, or one can have a central region is the porous structure. So, this is how you can define at the beginning of your 3D printing experiments that what kind of porous structure or porous scaffold that you want in these particular applications. And then you can do some one to one correlation. So, one to one correlation means suppose this is your input file, what is the output scaffolds that you are getting. So, input file your pore size may be 100 micron, your output file your individual pore size can be 90 micron, or your output file your pore size can be 120 micron. So, you are not getting essentially what is the 100 micron pore, that you are giving it as an input file the pore, or you can give certain pore to pore distance, this kind of pore to pore distance you define, let us say 50 micron, that is your input file. But in output file the pore to pore distance may be 40 micron because your pore size is already increased. So, those kind of design to product, that kind of one to one ratio, one has to see that how you can translate that. So, this is what we have published in Rapid Prototyping Journal in last in 2015. Now, before I finish that other things that I want to mention is that another case study says strontium substituted magnesium phosphate scaffold. Now, why strontium? Strontium is one of the strontium based drug like strontium renalate. It is very well known drug for treating osteoporosis. So, why magnesium? Magnesium is biodegradable. So, we want to develop some magnesium phosphate scaffolds which is biodegradable nature and which also can be used for the osteoporosis treatment. And then we started with the calcium magnesium phosphates, that kind of scaffold, and this calcium magnesium phosphate you have the tetracalcium phosphate, you have tetra tricalcium phosphate, you have alpha beta tricalcium phosphate, then you give this kind of phosphates, then you do the 3D printing and some post processing technique, and then post processing can be either by done sintering or can be post hardened. Now, in the sintering and post hardened, depending on what kind of chemical post hardening treatment essentially means, like you use this kind of 3.5 molar diammonium hydrogen phosphate solution and you immerse the scaffold for 1 hour. And once you immerse the scaffold for 1 hour, then after that you do this X-ray diffraction technique and you use whatever is the phases that is forming, that is either struvite phase, and then what is the reaction that is working, that is taking place during the chemical conversion. Your magnesium phosphate will react to sodium diammonium biphosphate and then it gives MgNH4 PO4 H2O, that is a production, that is a reaction product. Now, depending on whether you are doing sintering or whether you are doing post hardening, what you see here, you are getting a different strength properties. Now, from our application point of view, this particular scaffold Mg 2.5, strontium 0.5, PO4 whole 2, so essentially strontium is partially replacing magnesium and therefore, it is occupying the magnesium site, and then what you see here, that is a combination of compressive strength, flexural strength and tensile strength is better than other ceramic materials here, and this is a typical tensile stress response here. Now, this is a microcomputer tomography data. What you can see here, that this gives a very this last one gives a very nice 3-dimensional porosity distribution in the 3D scaffolds. And this is more clear here, this is a chemically converted, as you can see very clearly that pore distribution is much more clear. And why different color contrast is coming? Different color contrast is coming simply because these scaffolds have different type of phases, and each of the phase has a different X-ray absorption cross section. And if your X-ray absorption cross section is different, certainly it will give you a different contrast, and different color contrast is basically arises because of that. You can do lot of quantification also, like pore size, pore diameter, like Mg3PO4 to sintered and converted, and this pore size it can give rise to up to 130 or 140 micron, and as you can see that is the pore size, there is not much difference in terms of sintered and converted, only the porosity fraction is different, one is 15%, one is 22%, and sintered case it is 11.5 micron, converted case it is 9.6 micron. In the terms of the mechanical properties, you can do lot of other interesting things, and that is called Weibull modulus. Like Weibull modulus means strength reliability, and you can see the strength reliability values, that is M values. M is Weibull modulus, it is around 9 or 5. So, these values are very important because additive manufacturing is one of the newer techniques. So, here it is important to define what is the strength reliability of ceramics, because which is a major concern for other conventionally sintered materials. Now, in vitro ion release, as I said in the beginning of this particular case study, this strontium ion is expected to be released, and whether these strontium ions are released at all, and this is released when this magnesium 2 SR1 PO4 whole 2 is put it in that in vitro solution. Let us say it is a physiological medium, and this release is important because this is not absorbed, this should be released, and once it is releases, it stimulates the balance between the osteoblast and osteoclast cells in the bone. So, if in kind of osteoporotic bone, your osteoclast cells are more in number than osteoblast cells. So, strontium release actually will activate the biophysical processes to strike a balance between osteoblast cells and osteoclast cells. This work is now published in Acta Biomaterials, and this one can see more details, and it is published in Acta Biomaterials in 2016, and this is a collaboration of this work between ISC and a group in Germany. So, that is all about this 3D printing of the scaffolds or additive manufacturing of the scaffolds. Thank you.